Hello everyone, welcome to my talk. This is Tiancheng Sun from UC San Diego. Today I'm going to talk about our recent research on light stage super resolution, which focus on continuous high frequency relighting on human faces. Relighting human faces has been a central problem in computer graphics. More specifically, we capture the appearance of human faces using some devices, and then change the lightings and produce photorealistic relit rendering of the subject. LightStage represents an efficient solution for this problem. By programmatically activating and deactivating several LED lights arranged in a sphere while capturing synchronized images, it captures the full reflection field of the subject with hundreds of images within few seconds. These kind of data are called OLED data, or one light at a time data, since only one point light is turned on when each image is captured. Because light is additive, this OLED scan represents a set of lighting bases. The subject can be relit according to a novel environmental lighting by projecting that environment onto these lighting bases and performing a weighted summation. Here, we show an example OLED data and configuration of a light stage with 300 lights. We project the lighting to the latitude-longitude coordinates, and the blue dot is the only activated light on the light stage. The corresponding captured image under the light is shown in the right. As you can see, realistic high-frequency effects such as sharp casting shadows and specular highlights are presented in captured OLED images. Due to practical constraints, even the most sophisticated light stage only contains a few hundred lights that are spaced many degrees apart. In this configuration, the nearest light pairs are 11 degrees apart. This actually introduced problems when we relight image under new environments with high-frequency lightings. Here, we show two images which were lit by two adjacent LEDs on the light stage. If we render the image lit by a virtual LED lies in the middle of these two LEDs, the traditional linear blending method will generate ghosting artifacts on the shadows and the highlights. This is because we only have 300 LEDs on the light stage. The number of lights is still sufficient for us to perform relighting under soft environmental lightings, but it's too sparse to do relighting under all frequency. More specifically here, we cannot generate perfect images using OLED data and arbitrary directional light sources. Thus, the goal of this project is to super-sample the LEDs on the light stage and produce convincing relighting results under all possible lightings. Let's first review what has been done in the previous works. In last year's SIGGRAPH, we presented single-image portrait relighting. In this work, we captured several portraits under the light stage, applied traditional linear blending relighting to generate portrait pairs with different lightings, and used the generated pairs to train a portrait relighting network with a single portrait as the input. This work achieves portrait relighting under natural soft illumination. However, it does not focus on directional lighting. In fact, it fails to produce promising results under high-frequency lightings. Our current work can generate portrait pairs with higher quality in order to train the portrait relighting network. Another relevant work was from SIGGRAPH 2018. This work focused on general image relighting using neural networks. Given images under 5 fixed directional lighting, the network can generate images under new directional lightings. The network is trained using only synthetic data and can generalize well to real-world specular highlights. It seems very straightforward to apply this method to solve our problem. However, their network can only work on this hemisphere, and the input of the network is fixed to the images under specific lighting directions. Deep reflectance field from last year's SIGGRAPH also focused on a very similar problem. More specifically, they also want to generate portrait images under some specific directional lighting, but with only 2 images as input. As a result, their method can achieve consistent relighting of dynamic videos. In our work, we take the advantage of the full OLED data, which contains 300 images, and aim at more realistic image results. Our problem is formulated as this. Given an OLED, which contains images lit by all the LEDs on the light stage, we want to use a neural network to encode the reflecting field information, so that when given an arbitrary light direction, the network can predict the corresponding image lit by the query directional light. In other words, we want to upsample the lighting resolution on the light stage, so that we do not have to restrict ourselves to 300 physical LEDs on the light stage. However, as there are hundreds of LEDs on the light stage, it's not possible to feed all the OLED images into the network. Thus, given a query light direction, which is shown as the red dot here, we only choose the images of the neighboring LEDs to predict the image under the target light. To give a concrete example, we collect the neighboring images and their corresponding light directions. Using our neural network, we predict the image under the query light direction. Notice that as we move the query light, the input images and corresponding neighbors are also changing accordingly. Naively training this network will cause two problems. The first problem is about input neighbor selection. During training, we can only train on images that was lit by some real physical LEDs on the light stage. But during testing, our query light direction can be anywhere. This creates a mismatch of the light distance distribution between training and testing, which will likely introduce overfitting problems. This is mainly because the LEDs on the light stage are regularly distributed, so that the distance between neighbors always remain the same, and the distance distribution between training and testing differs a lot. In order to solve this problem, we utilize the idea of dropout when selecting the input lights. During training, we first select a larger set of neighbors, which is shown in yellow here, and then we randomly pick LEDs from this set as the input lights. In this way, the distance distribution between training and testing becomes more similar, and the prediction results are improved. Another problem is that during test time, our input set is dynamic. As shown here, when the red dot, the query light direction, moves, the blue light will enter the input set and the purple light will exit the input set. This abrupt change in the input will result in sudden change in the prediction image. We create a pooling method called Alias free pooling to solve this problem. We apply different weights on the input light depending on its distance to the query light, and set the weight at the boundary of the input set to be 0. In this way, even though the input images are changing, it is weighted as 0, and will not affect the final prediction. Here we show our detailed network structure. The encoder of our model takes as input a concatenation of the nearby OLED images and their light directions, which are processed by a series of convolution layers. The resulting encoded activations of these 8 inputs at each level are then combined using the alias free pooling and skip connected to the decoder. The decoder takes as input the query light direction, processes it with fully connected layers, and decodes the image using a series of transposed convolution layers, along with the skip connected encoder activations. We train our network using 16 different OLED image sets, covering different camera angles, genders, and skin tones. The output of our network is supervised using L1 loss. We also utilize progressive training to train our network, which stabilizes the training process. Now we show some results on our test data. As shown in the right side, when we move the query light direction along the equator of the light stage, the corresponding neighbors are selected from the OLED, and our network could produce realistic shadow movements on the person's face, without any flickering or ghosting artifacts. Our alias-free pooling technique essentially performs a weighted average activation. If we replace our alias-free pooling with a simple average pooling, the result will contain flickering when we move the light, as shown here in the bottom right. We also compared our results with some of the related work. We improved the method from Xu et al. With adaptive sampling, so that the inputs of the network becomes the same as ours. However, their network still contains flickering and ghosting artifacts, mainly because it is sensitive to the aliasing introduced when neighbors leave and enter the input set. The method from Mecca et al. Produces more pleasing results, without flickering or ghosting artifacts. However, the predicted images are more blurry than ours and does not keep the overall brightness. This is likely because their model is designed for fast and approximate video relighting and uses only 2 images as input, while our model has access to the entire OLED scan and is designed for high-quality rendering. An interesting question in light transport acquisition is how many images are needed to reconstruct the full light transport function. To address this question, we remove some lights from our training set and use only this subsample data during training and inference. In these figures, we present relit renderings using these subsampled light stages. We see that our model can produce accurate shadows even when the number of lights are halved. The ghosting artifacts only appear when the number of lights is reduced to 100. This enables us to construct light stages with fewer lights at lower cost, but still achieve similar relighting quality. A key benefit of our model is the ability to super-resolve an OLED scan with virtual lights at a higher resolution than the original light stage data, thereby enabling continuous high-frequency relighting with an essentially continuous light distribution. As shown in this video, we can now relight a person captured from a light stage under arbitrary light direction and produce sharp and realistic images. Please notice the highlights on the forehead and in the eyes, and the shadow near the nose. Highlights and casting shadows move smoothly as we change the light direction. OLED images can be linearly blended to reproduce images under a specific environment. This traditional approach may cause ghosting artifacts in shadows and specularities due to the finite sampling of light directions on the light stage. Although it is hard to notice when the light is low frequency, it can be significant when the environment contains high frequency lighting, such as the sun in the sky. These ghosting artifacts can be ameliorated by using our model. As shown in the video comparison, this approach produces images with sharp shadows and minimal ghosting when given a high-frequency environment, while linear blending does not. Our model can also generalize to people with different genders and skin tones, as shown in the video. Our method could suppress the ghosting artifacts in the shadow to minimum. Our model also allows us to control the softness of the shadow. Given a light direction, we can densely synthesize images corresponding to the light direction around it and average those images together to produce a rendering with realistic soft shadows. As shown in this video, our model is able to synthesize realistic shadows with controllable softness, which is not possible using traditional linear blending methods. In conclusion, we present a learning-based method to super-resolve the lights on the light stage. This enables us to infer the full reflectance field of the subject with discrete samples from the light stage. We achieve this with 2 key techniques. The dropout technique that randomly chooses the input images during training, and the alias repooling that suppresses artifacts on network activations. At last, we would like to thank all the people who have supported our project. And thank you very much for your attention.